Share screen. Hi everyone, my name is Chathuri Madakalapuge. I'm a PhD scholar from Monash University, Australia. I will be presenting on evaluation of current approaches for determination of moisture variation due to climatic effect in unbound payments within seals. I would like to acknowledge my research team, Dr. Dutta, Dr. Bodin, and Professor Kodikara. We all have experienced road failures happen all over the world due to various reasons. Environmental factors such as moisture and temperature have been identified as a major reasons for road failures, which affect both long-term and short-term pavement performance. Particularly, unbound pavement within seals are more susceptible for environmentally driven deteriorations. Unbound pavement within seals is one of the most common type of pavement in Australia. It comprises 90% of length of all surface road. It basically consists of three layers such as spread seal, unbound granular material as both base and subbase layers, and the subgrade. When the moisture condition changes in these layers, particularly unbound granular and the subgrade layers, the strength properties changes. More specifically, according to AUSTRA 2017 guidelines, when the degree of saturation in a UGM exceeds about 70%, the material can experience significant loss of strength or modulus. It can affect further large resilient and plastic deformation of both of these layers. Finally, it causes fatigue cracking and surface rotting. Let's see how this moisture varies in these unbound granular layer and the subgrade layer. Moisture can exchange between the surrounding environment and the pavement structure due to various scenarios, such as precipitation, evaporation, water table fluctuation, and etc., as shown in this picture. Since the spread seal is not 100% impermeable, water can percolate through the seal. Therefore, when prevailing climatic conditions such as rainfall, evaporation, temperature, relative humidity changes, moisture condition in these layers varies accordingly. This idealized model proposed by Kodikara 2018 qualitatively represents how moisture varies at each layers with the time. Here you can see the x-axis is time and the y-axis is the moisture content. After the construction of the pavement, the moisture condition at each layers come to the equilibrium position by initial drying or a wetting. We call the moisture content at this condition as the equilibrium moisture content. Even after reaching this value, the moisture content fluctuates around that value depending on the prevailing climatic condition. Therefore, the material properties can be affected by this temporal moisture variation. Thus, it is important to account these temporal moisture variations in the design process. The USA pavement design method can be identified as one of the advanced approaches that account the temporal variation of moisture into the pavement design. The USA design guide, the performance computation is done on the seasonal basis to incorporate the effect of the climatic condition on the behavior of the materials. As shown in this equation, the MR, which is the resilient modulus, is directly correlated to the degree of saturation. Therefore, to accurately determine the MR value, we need to predict the SR. For that purpose, USA has developed a sophisticated tool called Enhanced Integrated Climatic Model, EICM, which is a one-dimensional coupled heat and moisture flow program. It simulates the changes in temperature and the moisture in the pavement layers and the subgrade material in conjunction with climatic condition over several years of operation. It calculates the temperature, pore pressure, moisture content, and resilient modulus for each node in the profile for entire analysis period. It considers the climatic factors such as air temperature, wind speed, percentage sunshine, precipitation, and relative humidity. Let's see what is the current Australian approach to account the moisture variation due to the climatic factors. The current Australian pavement design guide has adopted a conservative approach to incorporate climatic factors into the pavement design. It provides the guidance to evaluate the strength or the stiffness parameters by testing at the moisture content likely to occur during the design period based on the annual rainfall and the drainage condition. However, the current Australian design practice does not account temporal moisture variation during the service life when evaluating the strength properties of these materials. The main reason for this is unavailability of an accurate model to predict the moisture variation that incorporate climatic factor variations. This became the key motivation to the current research project. The main objective of this project is to develop a practical approach that can predict the moisture variation to incorporate climatic effects for current Australian pavement design. So it develops a numerical model to predict the moisture variation over its service life by capturing essential physics. I would like to share some results of numerical modeling of sample test pavement constructed in New South Wales. This numerical model was developed to simulate the moisture flow and then to obtain the degree of saturation at each depth of the pavement layers by incorporating prevailing climatic factors using HYDROS 1D. The model test pavement was constructed as part of PhD research by Carter 2015 in New South Wales. It was constructed and continuously monitored for 2 years' time. As shown in here, it consists of basically 4 layers. The topmost layer is a bitumen emulsion prime seal, which is a thin spread seal, and both base and the sub-base layers are consist of granular material. And then we have a compacted subgrade, which is the topmost layer of the subgrade. And finally, we have a uncompacted subgrade. So this chart shows you a description of a permeability properties of each layer. The seal has a relatively low permeability in 2 into 10 to the power minus 5, and base layer also has 4 into 10 to the power minus 5 permeability, and both compacted and uncompacted subgrades are relatively impermeable. So this graph shows the water retention properties of each material. This is showing the climatic factor variation, which determines the top boundary condition. It shows the precipitation and evaporation variation throughout the simulation time period. The bottom boundary is defined by the water table depth. It also fluctuates during that time. This is the results that we obtained for the prediction of the degree of saturation variation in pavement layers at the middle of each layer. As you can see here, all the layers are reaching an equilibrium condition after some time by initial wetting or drying. As an example, the middle of the base layer, which is the unbound granular material, reaches around 60% of degree of saturation. And even after reaching that point, it fluctuates the moisture content around that value. Here you can see that it reaches 90% of degree of saturation. Therefore, this kind of simulation clearly predicts how the moisture varies during its service life. And this helps the designer to evaluate what are the expected moisture conditions. And finally, it can be concluded that this kind of prediction gives a clear understanding on how moisture variation would happen during the service life. Finally, it helped to improve the design to come up with a more safe and economical pavement design. So with that, I come to the end of my presentation. Thank you very much for your attention.